Welcome, everyone. Thank you for joining us for our June stargazing lecture, and thank you for coming back for an in-person event, or for those of you online, thank you for joining us on one of the various streaming sources where we're streaming this, YouTube and Facebook and Twitter. It's a pleasure to be with all of you again after a couple of years, so I appreciate you guys coming out today. We've got a great event planned for tonight. Just a couple of quick announcements before we start with our lecture. So this is part of a monthly lecture series. We will continue these lecture series for the foreseeable future. I haven't yet planned our events for July through the rest of the year, but I'm getting on it as soon as we start the weekend. So I'll have some posters up for the next few events coming soon. We also have a series of sister events called Astronomy on Tap. We are starting to host those in person again. It'll be our first event in person in a week and a half. We're hosting at a new location in Pasadena called the Dog House. Some of you may be familiar with it. It's in Old Town Pasadena, just off of Colorado. It's actually on a street called the Big Bang Theory Alley, which is kind of cool that we get to be associated with something that is, you know, the popularization of astronomy, as well as Caltech and so on and so forth. So it's called the Dog House. I'll have information online about it very soon. So we'll have one on Monday night, and we'll have one on the same week on Wednesday night, as part of the American Astronomical Society, which brings astronomers from all around the world. The meeting is happening in Pasadena that week. So there will be like 5,000 astronomers in town at the Pasadena Convention Center. There's also a bunch of events called the Pasadena City of Astronomy. There will be an event at the Convention Center on the Saturday preceding that. I'll have links on our website that provide context for that. So there's going to be a bunch of opportunities to do and listen to science in the next couple of weeks. But we'll have 2 Astronomy on Taps, and I'm still trying to figure out who will be speaking for that. It will be an outdoor venue. It's totally outside. It hosts about 100 people or so, and you can drink beer or have food and listen to science, and there will be pub trivia, and it's all free. I mean, the food and the drink aren't free, but like my science part of it is free. So I encourage you to check that out. And we'll have an Astronomy on Tap that's also up in the Eastern Sierra in the town of Bishop at the Mountain Rambler Observatory, or Mountain Rambler Brewery, not observatory, at the end of the month, and I'll have information on our website about that. So schedule of tonight, we'll get started in a moment. Our speaker will give roughly a 30 or so minute talk, and then we'll immediately jump into a Q&A panel consisting of Janosz, our speaker, as well as myself and a couple of other members of the department who work on different types of science. And then we'll open the questions up to all of you, so you can ask questions about the content of Janosz's presentation, as well as just questions that you may have about physics or astronomy or space science, and we'll do our best to come up with some reasonable responses to the questions that you throw at us. And then shortly after that, we'll open up the telescopes that are on the field behind us, so people can go check out what's in the sky. We have a couple of different telescopes. The only bright objects in the sky right now is the moon. The visible planets are all up in the early morning at like 4 in the morning, which is too early for me, or too late for me, maybe you as well. But there will be some deep sky objects that hopefully we can pierce through the clouds and be able to see as well. So I guess without further ado, I'll introduce our speaker. So Dr. Janosz Dewberry is joining us. He did his undergrad at Vassar, his PhD at Cambridge University in the UK, and then has done a series of postdocs. He was in Shanghai for a year, jointly between Shanghai and Ithaca, New York at Cornell. And then he has been at CETA, the Center for Canadian Institute for Theoretical Physics in Toronto for a year. And then he's been here as a visiting postdoc here at Caltech for the last year. So I'm very excited. Janosz is both a great scientist as well as a good friend. I'm really excited to introduce him because I've seen this talk and it's super cool, Planetquakes. And so please welcome our speaker tonight, Janosz.
Thank you, Cameron, for that introduction. And thank you again to all of you for showing up in person and to everyone online. Today, I'm going to be talking about an area of research that I've worked in for the last couple of years that is focused on waves and oscillations in gas giant planets like Jupiter and Saturn. Specifically, I'll be talking about how waves and oscillations in Jupiter and Saturn can allow these planets to interact with their environment, and in turn, how those interactions can tell us about Jupiter and Saturn's internal structures and their other intrinsic properties. So I'd like to start close to home. So if any of you live in California, you've probably experienced an earthquake. These can be scary and in some cases quite dangerous, but they're also very useful because they tell us a lot of information about what's beneath our feet. So when an earthquake happens, it launches lots of seismic waves that will propagate through the Earth's interior. And exactly how these waves propagate can tell us about the material that they're propagating through. So this diagram is illustrating a idea that if you have an earthquake, this launches a few different types of waves, which are denoted by different colors of line here. And some of these waves will be able to propagate through molten regions in the Earth's interior, whereas others will not. So if you have a seismic observing station that's located at different regions around the Earth, then whether or not different waves reach that seismic observing station can tell you about what they've passed through, and in turn help us map out what the internal structure of the Earth looks like. Astronomers also use seismology, except that we like to look inside the sun and other stars. So unfortunately, we can't go and actually place a seismograph on the surface of a star. But fortunately, the sun and many other stars are continually pulsating with what are called seismic oscillation modes, or normal mode oscillations. These are a little different from the propagating waves you might get right after an earthquake, in that they're essentially standing wave oscillations. So if you have, in this case, this diagram is depicting the propagation of acoustic waves, which are the equivalent of sound waves inside stars. And when these constructively interfere, they can produce a standing wave that will pulsate something like what's shown in this animation here. So this is an example of an acoustic oscillation that's produced by the constructive interference of propagating acoustic waves inside a model of a star. So this animation is showing, I should say, somewhat exaggerated distortion of the stellar surface by the pulsation of this oscillation mode. But it's important to note that oscillation modes also involve internal motions inside stars. So this cutout animation is showing perturbations to the gas density. And so you can see that the gas is disturbed inside the star as well as at the star's surface. Fundamental aspect of stellar oscillation modes, the reason they're so useful to astronomers, is that they have frequencies that will depend on the properties of the star that they're oscillating in. So because these oscillation modes have frequencies that are sensitive to the intrinsic properties of a star, that means that we can use them to actually learn about the stars that we're looking at. There's a whole field that's dedicated to this called astroseismology. That there have been some talks in this series that have focused on that. I won't talk too much more about solar or stellar oscillations in this talk, but I do want to highlight one example of how stellar oscillations have been used to infer properties of a very nearby star. So specifically, a couple decades ago, helioseismologists who study oscillation modes inside our sun used a very large number of acoustic oscillations like the one shown in this animation to map out the rotation inside the sun. So that's what's shown in this diagram here. This is a color map where the red corresponds to more rapid rotation and the blue corresponds to slower rotation. So if you were to look at the sun's surface, looking at sunspots or something else moving across the sun's surface, you could see visually that the equator rotates more rapidly than the poles. But it's the fact that these oscillation modes are sensitive to the rotation inside the sun that has allowed us to map out what the sun's rotation actually looks like as we travel to great depths inside the star. So we can use seismology to look inside stars. What about gas giant planets? So if any of you have attended some of the talks in this series about exoplanets, you may be aware that a large number of the planets that we've detected in other systems are like Jupiter and Saturn, very large and gaseous. So if we want to understand planets throughout the universe, it would be a good idea to make sure we have a very clear picture of the internal structures of the gas giants in our own backyard. And somewhat surprisingly, it actually turns out that this picture is still fairly murky. There's a lot of unanswered questions that I'll get into throughout the rest of my talk. This schematic diagram illustrates the historical picture that planetary scientists have had for the internal structure of specifically Saturn, although a similar picture has applied to what people thought about the interior of Jupiter. So planetary scientists have for a long time thought that Saturn basically consists of two things: a big envelope of mostly hydrogen and helium gas, and then beneath that, in the very center of Saturn, a solid core of rock and potentially ice. Whether or not this kind of a core actually exists is kind of important for theories of planet formation. And so planetary scientists have devoted quite a lot of effort to actually trying to detect this in Saturn and Jupiter as well. The main instruments that we have to look at and learn about Jupiter and Saturn are the satellites Juno and Cassini. So Juno is still orbiting Jupiter. Cassini is sadly no longer with us. It had a good long run around Saturn, and then a few years ago it was crashed into Saturn's atmosphere. And both of these satellites carried a lot of instruments to measure various things about Jupiter and Saturn. But they both, a lot of effort went into making sure that they can both very precisely measure the external gravity fields of their respective planets. And so this measurement of the external gravity field of a planet does provide some information about the outer layers of the planet that's being observed. But this is really limited to the outermost half or so of the planet's structure. So it would be great if we had some other ways to look inside Jupiter and Saturn. For the reasons that I described in introducing seismic oscillation modes, it would be great if we could observe oscillations in Jupiter and Saturn directly. Unfortunately, both Jupiter and Saturn are quite dim. And so actually seeing oscillations by just looking at lightness variations directly is a difficult task, although this has maybe been done. There's a potential observation of oscillations in Jupiter. On the other hand, Saturn has a really big set of rings, and this turns out to be incredibly useful. So for the last few years, I have worked in a field of research called Saturn ring seismology. This is an area that's founded on the idea that a subset of oscillation modes pulsating inside Saturn will produce some external time periodic perturbations to Saturn's gravity field that will in turn excite waves in Saturn's rings. And given that Cassini was orbiting Saturn for quite a long time, Cassini was able to actually look at these rings and confirm that we do indeed see lots of waves propagating. Most of the waves detected in Saturn's rings were detected during so-called occultations. This is where sunlight shines through the rings, and Cassini was able to measure how much of that light is extincted along its path. And so this provided a pretty resounding confirmation that oscillation modes in Saturn do indeed excite waves in the rings. And so this is very, very useful. One thing about this excitation mechanism that I want to emphasize is that if you have a wave in the rings that is excited by a given internal oscillation inside Saturn, the radiolocation where this wave is excited will depend on the frequency of the mode that excites it. So this is kind of similar to situation if you're trying to push somebody on a swing. If they only want to swing a little bit, then you have to stand very close and push very frequently. But on the other hand, if they want to swing really high, then you have to stand further back and push much less frequently. So similarly, oscillation modes in Saturn, if they have lower frequencies, will in general excite waves that are further out in the rings, although I am glossing over a few details there. With some important exceptions, most of the waves that are excited in Saturn's rings by internal oscillations in Saturn are produced by so-called fundamental modes, or F modes for short. These are physically the most similar to surface waves on the ocean. And they're able to excite waves in Saturn's rings because they typically involve large perturbations to the gravity field of the planet or star that they're pulsating in. So this color map here shows negative and positive perturbations to the gravity field produced by a fundamental mode that I've calculated for a model of a planet. Like other oscillation modes, F modes are sensitive to the internal properties of the planet or the star. The animation on the left here is showing an F mode for a very simple model of a planet that has no core whatsoever. The animation in the middle is showing the same F mode, but one that I've calculated for a model that has a core enhancement to the gas density. And so you can see that there's some differences in the spatial structure of the oscillation. And there's also some small differences in the frequency of the oscillation mode, although you can't really see that in this animation. You can get even larger differences in both the oscillation structure and its frequency if you include the effects of Saturn's very rapid rotation. And I'll come back to this a little bit later on in the talk. So to recap, the basic steps underlying Saturn ring seismology is to use Cassini data to detect waves in Saturn's rings, then identify those waves with excitation by oscillation modes inside Saturn. And then the last and most interesting, but also potentially most difficult task is to turn around and use the information that we've gained about these oscillations to learn about Saturn's internal structure and intrinsic properties. So what have we actually learned from Saturn ring seismology? So a puzzle that came out pretty early on, soon after detections of waves by Cassini, was that there are more waves in Saturn's rings than can be explained by the F modes alone. So there have to be some other type of internal oscillations that are exciting these additional waves. And so one of my collaborators, Professor Jim Fuller, who's here at Caltech, showed back in 2014 that these additional waves in Saturn's rings can be explained by so-called internal gravity modes, or G modes. These are not to be confused with gravitational waves. These are oscillations that are related to buoyancy in the gas. And so as you can see from this animation, this is again showing gravitational perturbations, but for an example of a G mode. These oscillations have a lot of structure in the very deep interior of Saturn. So identifying specific G modes could be really helpful for learning about conditions in the very deep interior. Just last year, another collaborator of mine, Chris Mankiewicz, worked with Jim to use G mode seismology to make a somewhat surprising discovery, which is that Saturn's core is actually very diffuse. So the picture on the left is showing the traditional understanding of Saturn's structure that I introduced with a diagram earlier. Here, the y-axis is showing density, and then the x-axis is showing radius in the planet. So this would be the center of Saturn. This would be its surface. And so with this model with a solid core, you have a really strong density enhancement that drops off very quickly. And then you have a gaseous envelope outside that. But what Chris and Jim's work showed was that it's actually looking more and more like Saturn has a much more diffuse core. So there is some density enhancement at the center, but it's much smaller than the enhancement that would be associated with a solid core. And so this updates the picture that planetary scientists have of giant planets in our solar system. So rather than having this solid rock at the center of Saturn, it's more likely that Saturn is actually mostly gaseous all the way down, which is somewhat surprising and interesting in light of theories of planet formation. You might notice from this diagram that other lines of data have also pointed towards Jupiter having a similar structure. So it doesn't look like there's a compact core there either. What else can we learn from Saturn ring seismology? So an area that I have focused on pretty heavily is the effects of rotation on oscillation modes in general, and specifically in Saturn. So as I mentioned earlier, Saturn's rotation can have a fairly significant effect on its oscillation modes. This happens because of two main effects. So first of all, rotation will act to flatten a planet or a star. It's illustrated by this diagram here. This is showing the density inside a model of a planet or a star that is rotating more and more rapidly. And there's additionally an additional force associated with rotation called the Coriolis force that will also modify oscillations. So we know that Saturn rotates pretty rapidly, but historically it's actually been pretty difficult to measure this rotation rate directly. And so a couple of years ago, Chris showed, using, again, seismology involving F modes in Saturn, that Saturn has a bulk rotation rate, so its mean rotation rate, that's around 40% of what's called a breakup angular velocity. So this breakup angular velocity is the rotation rate at which, if a planet or star were to rotate any more rapidly, then it would start to spew away matter at its equator. It would come apart. And so 40% of that is quite rapid. On top of this very rapid bulk rotation, Saturn also has some fairly strong atmospheric winds. So that's shown in this plot on the left. This plot on the y-axis is showing latitude with a 0 corresponding to the equator in the planet. And then on the x-axis is the wind speeds that are observed at Saturn's surface. And so you can see that at Saturn's equator, there's a fairly strong equatorial jet. And some work that I was involved in last year, and I'm still working on, has shown that these zonal winds in Saturn's atmosphere can also significantly affect Saturn's oscillation modes in a way that is detectable in Cassini data. So a project that I'm involved in with Chris Mankiewicz and Jim Fuller is to, like I described for the inversion of the sun's rotation rate, try and use Saturn ring seismology to map out the internal structure of rotation in Saturn. So I've talked a lot about Saturn. What about Jupiter? So Jupiter does also have some rings. Unfortunately, they're very faint, so it doesn't provide the same opportunities for ring seismology that Saturn's rings do. On the other hand, one thing that Jupiter has in abundance is moons. And it turns out that Jupiter's gravitational interactions with some of its moons can also provide some potentially very interesting information about how Jupiter is structured and its properties. So two massive objects that are interacting gravitationally will, in general, interact via what's called a tidal interaction. So the closest example of a tidal interaction that we have here on Earth is Earth's tidal interaction with our moon. So the moon will pull on the Earth, and this raises bulge. So in this case, this animation is showing water that's being lifted towards the moon. This is not something special about water, it's just that water is more easily pulled than the solid Earth beneath our feet. And so the Earth's rotation through this tidal bulge will lead to the tides that we observe on our beaches. And this type of tidal interaction happens throughout astrophysics. So one project that I worked on relatively recently has been focused on the actual shape that this tidal bulge takes in gas giant planets that are rotating as rapidly as Jupiter or Saturn. So these two animations here show the tidal bulge that I've calculated for satellites that are identical in both cases, except that on the bottom, this is a planet that's rotating with around Saturn's rotation rate. So again, 40% of this breakup angular velocity. Whereas on the top, this is a planet that has no rotation. So it's if the moon weren't there, it would just be perfectly spherically symmetric. And so you'll notice that these two animations actually look pretty similar. So you can see some flattening that's due to the rotation in the bottom animation. But by and large, these tidal bulges look more or less the same. But there are actually some pretty significant differences between these two if you compare them on a quantitative level. And the differences have been and are detectable in, for instance, Juno measurements of the tidal bulges raised on Jupiter. You can also potentially get some more interestingly shaped tidal bulges if a satellite moon is close to what's called a resonance. So in this case, I've tuned the orbital frequency of the satellite moon so that it comes very close to the natural frequency of oscillation for, again, an oscillation mode of the planet that's being considered. And in this case, you can see that the tidal bulge that this produces is quite different. It takes on a shape that's kind of similar to the overall structure of the oscillation mode because this mode is being forced very strongly by this moon. And so this effect is a little exaggerated in this animation because I've tuned the moon's orbital frequency. But this is actually something that has been potentially observed in Juno data for Jupiter as well. So it may be that Jupiter is involved in a resonant interaction with Io of this kind. I'm going to finish there. So hopefully I have convinced you that oscillations in planets and stars are interesting. If there's one thing to take away, it would be that seismic oscillations can tell us about stellar and planetary interiors. In Saturn's case in particular, Saturn ring seismology can and has provided information about Saturn's internal structure, its bulk rotation rate, and also its atmospheric winds. And then lastly, Jupiter and Saturn's interactions with their satellite moons can also tell us a little more about these planets. Thank you very much for your time. Are there any questions? I actually can't see the Zoom, so I don't know if there's anything on YouTube. Very low. Sorry. Yeah. So the question is, what are the chances of doing this kind of a measurement in another system? And so all of the work that I've described here has been made possible because of these satellites that we have around Jupiter and Saturn. So unless we can send a satellite to a planet in another system, it would be unlikely that we'd be able to do this kind of measurement anytime soon. There have been some studies of tidal interactions of planets and other systems, but this doesn't provide anywhere near the detail you need to make the kind of measurements that Juno has made for Jupiter. So just to make sure I heard, so you're asking if you have a fully isolated planet with no interactions, how would you learn about it? So there are a number of mechanisms inside planets and stars that can excite oscillations. So for instance, in Saturn, it's still unclear exactly what excites the oscillation modes that we see in its rings. But for instance, in the sun, there's a process called convection that excites most of the oscillations that we see. And so you don't really need external interactions to see those for stars. For planets, it would potentially be very difficult to observe this kind of thing directly. It's, like I said, because of the interactions of these planets with their environments that we're actually able to detect these oscillations. In Jupiter's case, there is a potential detection of oscillations that have been made just by looking at it, but this is still being debated. It's not clear whether that's actually an oscillation or not.
My understanding might be a little bit fuzzy, but I believe that we sort of previously understood that gas giants are created with like core nucleated accretion.
Mm-hmm.
Does this change kind of our thinking about that, or like confirm or deny, or anything?
So, okay, so the question was, does this change or alter our understanding of how planets form? Is that right? Yeah. So I'm not an expert in this area. I haven't really studied planet formation in any great detail. My understanding is that this is not a huge. This is something that is entirely possible within the existing theories of planet formation, but it does kind of push theories in one direction or another. You had a question, I think? Oh, it was the same question. Yeah.
The question I had is, you were able to show like Jupiter and Saturn, they have counterintuitively very diffuse cores.
Mm-hmm.
And so taking that data, is that something that you would be able to extrapolate to other similar gas giants? I know you said in our own, outside of our own system, we may not be able to really assess that properly, but is that something that's incidental, or do you think that's something more of a general finding that may be applicable to other gas giants?
Mm-hmm. So the question was this finding of Chris and Jim's that Saturn's core is diffuse and similar observations of the core in Jupiter, whether that can be extrapolated and applied to planets outside our solar system. Is that right? Yeah. So I think so. I think that's an active area of research. I think there are a lot of important differences between a lot of the exoplanets that are observed outside our solar system. Even though they are still gas giants, they are different in a lot of respects. So there may not be direct transferal of that inference, but it does help us in the right direction.
There are a couple of questions online that I'd like to ask, if that's okay.
Please. Yeah.
There's a question from Andrew Anstapa who asks, would it be feasible to, or also would it be ethical to drop a nuclear device of a known power on a gas giant to actually create substantially more intense seismic oscillations? Well, first of all, would you learn anything more about that structure by inducing like a known power perturbation from some sort of artificial means like a nuclear weapon? And yeah, would that also be feasible or ethical to do?
So I have no idea about the feasibility. I'm not an expert in nuclear weapons or delivering them to other planets. It's interesting question because one of the theories actually for how these oscillations are excited in Saturn is that they are produced by impacts. So some very large object crashes into Saturn and that sets off a bunch of oscillations, same way ringing a bell leaves the bell ringing for a little while afterward. So presumably you would, any kind of impact will lead to some oscillations. Yeah.
Related to that, there was I forget the exact name, but I'm sure I can be corrected by people either on our online or in-person audience, but there was a comet that struck Jupiter. Was it Shoemaker-Levy? It was Shoemaker-Levy, struck Jupiter in 1995-ish, sometime in the 90s. Do we have data? I mean, I realize much of the observational data that you were providing was based on Cassini and Juno, which have not been up there since then, but do we have any kind of maybe lower resolution data from that period when that strike occurred? Because I know a ton of telescopes were pointed at Jupiter during that period. Like, could we calibrate some of these methods based on that impact or learn anything based on the impact that occurred then? Or would we have to wait for another event of a similar kind of magnitude to strike today to learn something from it?
So I'm not really sure about the data availability for that event. I do know that I don't think was really large enough to immediately produce the type of oscillations that you'd actually be able to see in Jupiter. So you'd need continual bombardment or something larger to produce detectable modes.
Are there other questions from the audience here? I think there's some more questions here, but I figure I should give the people who turned out in person priority over the people who's sitting at their computers online. Okay. Oh, just rubbing your nose. Okay. There's another question online. Well, okay, before I try and process that and convert it, I have a question. You were talking about the previous kind of paradigm was for having some sort of solid core structure. And based on some of the recent work that was done showed that it's more of a continuous gradient in density as you go to the interior. And that it seemed like you were interpreting that as just an increase in gas density, but is it possible that you wouldn't necessarily be able to probe the difference between gas or it turning into a liquid, which is also a fluid and behaves according to fluid dynamics? Like, would you be sensitive to an interface between like a liquid core? Or is it only a solid core that's not going to respond to fluid, like seismic wave, P waves and S waves?
Yeah, so these seismic oscillations, they don't really care so much whether it's a gas or a liquid. The thing that will differ is whether it's if the where was that plot? Here. Yeah, so The oscillations are mostly just sensitive to this gas density and a few other properties of the planet. So whether or not that you'd be able to differentiate between the two is kind of difficult to say. There are a lot of uncertainties about the equations of state that you get for pressures this high in the center of Saturn. So that's an area of ongoing work.
Okay. Oh.
Can you determine anything about the chemical composition in the fuzzy core?
Well, so the whole reason this core is fuzzy because there's a gradual gradient in the composition of heavy elements as you go to larger and larger radii. Chris would be the person to ask about specific constraints on the chemical composition for Jupiter, or for Saturn, excuse me. But yeah, there are some things that we can learn there as well.
This was already kind of brought up for extrapolating to other systems. Are there any other future missions planned for Neptune or Uranus? I thought there was a big hoopla about Uranus in the news in the last couple of months. Will we have the ability to take similar observations on other gas giants within our solar system to confirm whether or not this kind of holds for other systems?
I hope so. Yeah, I think there's a lot of attention that's being given to Uranus and Neptune, and there is a possibility of similar types of seismological studies there.
Cool. Was there another question? Yeah.
I just have a comment regarding the nuking Saturn idea. We were actually discussing a paper today at our group meeting where they detected another asteroid impact on Jupiter. And that energy was estimated to be about 2 megaton, a 2 megaton impact. So, and that's actually far smaller than Shoemaker-Levy, which cannot excite oscillations to detectable levels. So even though it might be a lot of fun to nuke a gas giant, it wouldn't be scientifically very valuable.
That's useful to know. Useful to know. So don't have people flinging nuclear weapons at gas giants in the name of science anyway. Okay, I think those are all the questions for now. So what we'll do, well, first of all, let's thank our speaker. The wonderful presentation, Dr. Dewberry. Okay, so now what we'll do, there will be a brief transition period. We're going to set up a table here for like a broader Q&A where you can ask questions of Janosz, myself, and a couple of other members of the department. But at the same time, we've got telescopes set up on the adjacent athletic fields here. Sorry, online audience, you don't get to look through the telescopes. I haven't set up that technology just yet. But if you want to go check those out, you're welcome to do so. We've got a number of different targets set up, but we'll be here. So if you go out there, check out a few targets, want to come back or head home or whatever, we'll be ready to go. So, and just a brief reminder that our next events are another public lecture next month, and then Astronomy on Tap in person at the Dog House in a week and a half. Monday night and Wednesday night. I'll have the details online very soon. I'm not sure we're going to be able to live stream those, but I'll do my best to try and do that to the online audience. Okay. Okay. We'll set up and start our Q&A here in about 5 minutes, but you can go check things out outside if you want to. I'm going to move this camera as well since it's directed up kind of askew. One moment, guys. We're just getting set up. We'll get started in about a minute. I guess this will do. Thank you for sticking around, audience member, and our online audience members. So we encourage you to ask your questions. I don't even know if I'm in the camera frame here. We encourage you to ask your questions through the online interface, either through Facebook or through YouTube, and we will do our best to respond. This can be on anything related to astronomy or physics or space science, or something that hopefully we can respond to. Not anything related to the Johnny Depp Amber Heard trial or other public pieces of news like that. So and can be about the content of Janosz's talk. So there were a few more questions that I didn't necessarily get to in the content of the relevant to the content of the presentation. And one was, can we do anything similar with not just planets like gas giants? Obviously, you demonstrated at the beginning of your presentation stuff about the Earth and having the liquid mantle, and earthquakes can reveal stuff. But what can we learn about other rocky planets like Mercury or Venus or Mars? And what have we learned? I know there's someone mentioned the InSight lander that's sitting on the surface of Mars and has a seismograph and has been probing it for the last couple of years, I think. Yeah, do you have any insight on that?
So I don't have a lot of insight on it, but Mars seismology is a thing of the very near future. That is something that people are actively working on and will be providing information pretty soon.
Sorry, audience members, trying to get through the comments while leading the Q&A is a challenge here. Do you have any questions? Okay, no worries. Just let me know when you do. Hand you the microphone. Okay, so YouTube, about Facebook. Yeah, oh, okay, great. Sure.
Yeah, I'm curious how you guys start doing research in a field. Like, how do you identify the field? How do you find out what are the most important papers in there? And especially if you can tell me the new tools that you have, like Google Scholar and things like that, how you use those.
Yeah, so I mean, the biggest tool are some online databases of recent and previous papers. So there's a website called The Archive that astronomers post their preprints to. And so you look at this, you see what people are doing. There's also Harvard maintains an online database of astrophysics research papers that dates back, many years. And so this is where
we go to get our feet wet with a new field. So it's just a lot of time reading through different papers and seeing which papers those cite and get cited by, and then digging your way through the previous literature.
So, is it just on? Okay. I also want to make a plug for this website called Astrobytes. So if you're not an active researcher, but you are still interested in sort of the forefront of astronomy research, astrobytes.org is a great website. It's run by grad students. It's an international collaboration of grad students. And the whole goal is to take those papers that are on the archive, these like preprint papers, and write bite-sized summaries that folks can actually understand. And I think it's a great resource. Like I check Astrobytes every day because it helps me learn about other fields. So otherwise, reading a paper in another field takes me a solid several hours because it's so much jargon in another subfield that I don't understand. And so Astrobytes, I think, is a great way to break that down. So just putting it out there. Yes, astrobytes.org. Check us out. We also do interviews with astronomers. We do sort of current event pieces about astronomy. So definitely a cool thing to check out.
Excellent question. Do you have anything to add, Nick? Okay. Okay, so one thing that we didn't get a chance to do is each kind of introduce ourselves. I bypassed that and got caught up in questions already. So Janosz, I think everyone's familiar with Janosz, given the nature of his presentation. Excellent presentation. Nicholas, would you like to give a short introduction of yourself and what sort of science you work on?
Sure, yeah. Hello, everyone. My name is Nicholas.
I'm not sure it's on. Yeah, go ahead.
Yeah, thanks. Sorry about that. My name is Nicholas. I'm a second-year graduate student here in physics, and I work with Jim Fuller, one of the collaborators that Janosz mentioned. And I basically work on stellar oscillations as well, specifically sort of red giant oscillations. And I have a lot of interest in, trying to understand how we can use the oscillations we see from sort of these very evolved stars to understand sort of the history of that star and what's inside the star and what its core looks like. And in addition, I also have a lot of interest in things like the dense environments of globular star clusters, where stars are constantly interacting with each other, and you can get a lot of very interesting phenomena. But I guess I'll leave it there. There's a lot to talk about.
Thanks, Nicholas. Cameron, do you want to? You're technically next in the lineup. All right. My name is Mia Dulles Reyes. I actually just defended my PhD, so I guess I'm Dr. Dulles Reyes now.
Congratulations, Dr. Dulles Reyes.
So I study the chemical evolution of nearby dwarf galaxies. So these are really low mass galaxies that are sort of baby galaxies. And so understanding how these low mass galaxies form and evolve is actually really crucial for understanding how more massive galaxies like our Milky Way came to be. So I study sort of how these galaxies evolve, and I also use these galaxies as a tool to do what's called galactic archaeology. So I won't go into the details of it, but it is pretty cool. Just putting that out there. I don't do anything with planets, unfortunately. So if you have planet questions, that's the end of the table that you need to look at.
And yeah, sorry, I'm not just checking my phone. I'm trying to keep tabs on the comments from people online. Yeah, so I'm Dr. Cameron Hummels. I got my PhD too long ago, sadly. And I do research primarily in computational modeling of large swaths of the universe to follow the evolution of kind of the buildup of structures like galaxies, like what Mia studies. Sometimes smaller galaxies like she studies, sometimes more massive galaxies like our own Milky Way galaxy. But usually there's a need for doing this computational modeling because observations alone are restrictive. We've only been observing galaxies, or recognizing that we were observing galaxies for the last 100 years or so. And the timescales associated with how long it takes for these things to change substantially are very, very long. So as an example of that, the Earth orbits around the sun, as people generally all agree. And the Earth takes 1 year to make one orbit around the sun. That's how we define a year. But our entire solar system, composed of the sun and the Earth and the other various planets in the solar system, takes about 250 million years to make one orbit around the center of the Milky Way. So that gives you kind of an idea of the timescales associated with that. So if we had been around and watching other galaxies for hundreds of millions or billions of years, we could see how they changed over those kind of timescales. But given that we've only been looking at them for about 100 years, which is like the blink of an eye to those galaxies. We have to rely on other methods, like computer methods, where we can artificially speed up time in our simulations to see how they change and form and potentially die, to use these sort of analogies with other organisms. So yeah, so I mostly do that sort of work and try and understand these things from a theoretical perspective. Oh, you have some fans, Mia, some people reaching out to you.
Oh,
So seeking more
are you?
discussion later on. I'm on, oh yeah, what, go ahead, and I'm on Facebook here. So I'm jumping
Cool.
back.
I
and
will
forth.
monitor YouTube, and Cameron
Okay.
will monitor Facebook, and between the two of us, we have some good questions on YouTube actually. Yeah, let's see. Okay, so in the movie 2010, Space Odyssey, at the conclusion, Jupiter ignites and becomes a star. Is Jupiter big enough to become a star or a brown dwarf?
First, and then to you, sir.
No.
Yeah, I think people often say things like, Jupiter is a failed star. This is, I think you have to have many, many times the mass of Jupiter to even approach something which could be a star.
More than 100 times. So
Yeah, something like that. It's like, yeah. It's I guess one thing which is kind of interesting though about stars is that there is this range, of masses for which the planet or the brown dwarf doesn't really get bigger. So, I think if you keep adding mass to Jupiter, it's not going to get sort of bigger in size in the way that you might expect with like Plato or something. It's so I guess like, objects which are really close to being stars, like real failed stars like brown dwarfs, can be many, many, many times the mass of Jupiter, but they will be sort of like not so much bigger. Anyone else want to say anything about it?
I want to chime in. So that's a good question. And, for the most part, Arthur C. Clarke did a really good job of the science in 2001 in that series. I really appreciate it because some science fiction can go really, well, actually our last Astronomy on Tap was about the science of Star Trek and the science of Star Wars. And Star Trek, I think, is a little bit more accurate than Star Wars in terms of trying to base things in reality. But kind of to generalize something that was alluded to by my colleagues here, structures in the universe tend to clump on very different scales. So if you have a gravitationally bound cloud that starts to collapse under its own gravity, which is a pretty common occurrence in the universe, and that's nominally the sorts of things that we study are the collapsed things as opposed to the voids between things, although those are interesting too in a different way. You get a distribution of the sizes of the structures that form, and you get, as you can imagine, like if I drop a big clay pot on the ground and it shatters and it fragments into a bunch of different pieces, the same thing is kind of happening with these collapsing gas clouds, that they fragment into smaller and smaller clumps. They aren't pottery shards, but they're clumps of gas. But the overwhelming thing that you find is you get a lot more small things than you get large things. So if you drop a pottery clay pot, you'll get lots of little sand grains that shatter out of that and fewer large shards. And it's the same thing with this collapsing gas cloud, that you get lots and lots of little tiny gas clouds, like the size of Jupiter or the size of even smaller clouds. And you get very few gas clouds that are really big chunks, like are going to be a supermassive star or something like that, more massive than the sun. And so there's this whole continuum, though, of sizes of these clouds. And some of them, the smallest ones, end up not being sufficient to form, to have the pressures and energies at their cores necessary to start nuclear fusion, which is kind of the definition that we rely on for something being a star. And then there are some things that are more massive than that start to form nuclear fusion in their cores, and those become stars. And then there's really, really big boys that can do all kinds of crazy nuclear fusion, and sometimes won't even hold together initially because it's so explosive that they turn into a special kind of supernova. So yeah, there's a whole continuum. And so, yeah, I don't know. I just wanted to add that because I think it's interesting to kind of think about, instead of that there are these discrete categories of things. It's really just a continuum. And in some ways, those categories that we invoke are somewhat arbitrary. So do you want to add anything, Mia? Oh, monitor. Oh, yeah. So a great question. Throw more questions at us. I haven't been monitoring because I've been too busy yapping here. Okay. There's a question from Mark McCann on Facebook. Do you know the size of the black holes at the center of these small galaxies? Perhaps this is for you. Perhaps this is for the galaxy side of the table, as opposed to the stellar and planetary side of the table. Do we know the size?
Sort of. We sort of know the sizes of some of these black holes. I mean, for the most part, so actually it's an ongoing question whether, like, how many of these small galaxies actually have black holes at their center. So this is sort of an ongoing area of research. In the last few years, actually in the last month or so, we've found that there are actually a lot more of these dwarf galaxies that have active black holes at their center. So before we thought that maybe there was a cutoff that's, maybe bigger than a lot of these dwarf galaxies where you start seeing black holes, but now we're seeing more and more at even smaller, in even smaller galaxies. The sizes are a little difficult to measure, but for these dwarf galaxy black holes that we do see, we think that they probably, for the most part, scale with the overall size of the galaxy. So in the Milky Way's supermassive Sagittarius A star is 10 to the 6?
Yeah, I think it's a
few times. Okay, so in the Milky Way, in the mass of stars in the Milky Way is on the order of 10 to the 11. So that's 100 billion stars times the mass of the sun. So you can think of, if you had 100 billion suns, that's sort of the overall size of the Milky Way. The black hole at the center of the Milky Way is on the order of 1 million suns in terms of mass. And that mostly scales as you go to lower and lower masses. So if you have a black hole, if you have a galaxy that's 100 times less massive than the Milky Way, then its black hole is also going to be 100 times less massive than the black hole in the Milky Way. Although we're starting to realize that as we discover more and more of these black holes in small galaxies, that there are actually some that are sort of abnormally large, that have abnormally large black holes. And so this is still an ongoing thing. Like, this is quite a new result that I think people are still trying to wrap their heads around, but it could be really cool. So I hope that answered your question very thoroughly.
Yeah, excellent job, Mia. Yeah, it's definitely a challenging problem because it's challenging to study the black holes in the interiors of galaxies, because usually you're inferring the size of them from kind of indirect means. Everyone's familiar with the idea that a black hole, is for the most part black from the core of it, because light can't escape. That's what makes it a black hole. But then you can infer the mass of it based on how quickly light is traveling around, or objects are traveling around it, or how quick, or lensing effects, or various other things, how energetically stuff is getting flung out from the material that's close to it, that sort of thing. So, but it's definitely a challenging problem. So, other questions? Yeah.
All right, we have, let's see, a question. All right, I'll sort of just go backwards in time, from eFont on YouTube. Is there any sort of scientific legitimacy and or possibility to hypothetical quasi-stars? So it is not, there are things that are called quasi-stellar objects, or quasars for short, and those are not actually stars at all. They're galaxies that have really active black holes in their center. Other than that, there are things that are sort of like stars, but not quite. And these include things like brown dwarfs, which we just talked about, which are like stars, but smaller. They're so small that they don't actually start nuclear fusion the way stars do. Other than that, I'm not quite sure what is meant by quasi-stars. Oh, here we go. Hold on a second.
I just looked on Wikipedia, and it seems like people have considered this sort of object. Apparently, what this is basically a stellar-like object that is maybe 10 to the 3 or like 1,000 solar masses, but instead of being powered by hydrogen burning or some kind of burning of some element, it's instead powered by accretion onto a black hole. I've not really heard of anything like this. I guess it seems like plausible that it could be something that could happen, but I don't really know anything specific. Anyone have any? Comments about this?
Well, so I'm just wondering, is this is accretion that's sort of spherically symmetric onto the black hole?
Yes.
Because one aspect of accretion onto black holes is that generally gas that's moving towards a black hole will have some angular momentum, and so it spreads out into something more like a disk or a torus or something. So having this kind of a star with spherically symmetric accretion is seems unlikely to me, but this is not something I've heard much about.
Sort of early history of the universe kind of stuff. I do, there are things which are sort of more, people sort of talk about a little bit more, so things like population 3 stars, which sort of have more traditional mechanisms for burning, and these are basically, the stars that are the youngest are called population 1, and then there's population 2, and then population 3 is thought to be sort of these oldest stars, which can be much more massive. I've also heard like sort of very speculative things from some group out of Michigan, actually, that if there's dark matter and dark matter can annihilate, then this can create these weird stellar objects as well. Honestly, this is all sort of quite speculative. I think there's not very much direct evidence for stuff like this, and people sort of oftentimes discuss things that seem like fun physical configurations to talk about, I guess. Yeah. Do you have any comments?
I missed what was happening. I was checking outside.
We were discussing quasi-stars. So it looks like we have a couple more folks in the in-person audience. So if you have any questions about astronomy at all, feel free to ask.
Lay it on us. But there's still questions that
Yeah,
are coming in from our online
If
audience.
you want to think more about what questions you're asking, that's fine too.
Do you have any more? I've got one that I can ask here, but
Yeah, from Stephen Schreier on YouTube. Is there any scientific instrumentation that can observe the opposite side of the Milky Way galaxy? That's a great question. It's really hard to do. There's a lot of stuff going on in the middle of the galaxy, which makes it hard to see through. The biggest issue is dust. Fortunately, we can get through a lot of the dust by observing in longer infrared wavelengths. And so people have made pretty precise maps, even of the very center of the Milky Way, by using these infrared wavelengths for imaging. And you can sort of see to the other side of the Milky Way. It's just hard because then the issue is there are a lot of stars in the way. So you can see through the dust by looking at other wavelengths, but then there's just so many stars in the front that you really can't see that many stars that are in the distance. I think Cameron is about to draw a very helpful
I'm just
diagram.
I don't even know if this is gonna show up on the video well enough that people can recognize it, but I always find that I learn well from a visual demonstration of what we're talking about. So you
Sounds
feel
good.
free to keep talking, but I was just gonna kind of like, oh, I'm a horrible illustrator. Why did I agree to do this? But this is, something like this. I don't know if that's visible. Is that it?
It's kind of hard to see.
Oh, it looks like crap on this thing. Okay, well, maybe I'll stop. The point is that, the Milky Way galaxy, obviously we have a fixed perspective on the Milky Way galaxy because we exist within the Milky Way galaxy. But you can kind of think of it like famous pictures of the Andromeda galaxy, or even just the stereotypical kind of like spiral, pinwheely kind of looking structure on the sky. The example that I always like to use is like a fried egg. Like there's the white disc part and then the yolk in the center. So it's kind of a 2-component part. And just imagine that we as an entire planet and solar system sit about halfway out in the white part of that fried egg. And the question was like, can we observe the other side of the fried egg, like on the other side of the yolk? And as Mia said exactly correctly, it's just super difficult because like
There's so much crap.
there's
in
so
that
much
yolk.
there's so much stuff in the way. Yeah, absolutely. And yeah, dust and stars, and in fact, it's referred to as the zone of avoidance in observational ease because there's too many stars. You just can't see through the disk. So anyway.
So can you use gravitational lensing of the black hole to observe the background?
Oh, that's a good
Oh,
question.
That's a good question. So the main issue, I think, with that, and I am not a gravitational lensing expert, so I am not 100% sure, but my gut instinct is that would be really difficult to do. So in order for gravitational lensing to work well, you either need a really, really large mass, or you need the perfect alignment. So you need like the lens to be perfectly in line in just the right way with the thing behind it. So when we say a really big mass, we mean even much bigger than the what did you say? Few million times the mass of the sun, which is what the black hole is. So we're talking like clusters of galaxies. So many billions, trillions of times the mass of the sun. Or you can, or as I said, you could do it with very, very precise measurements and like the perfect alignment. And that's hard to do again, because there's just so much crap around the black hole in the center of the Milky Way. That's a great question though.
Yeah.
Gravitational lensing is very cool and very mathematically intense. So, oh yeah, Nicholas, go ahead.
I guess I just want to put a few numbers to how challenging it is to observe, stars that are sort of in the galactic center. So I think one number that's been quoted is people like astronomers will say something like, there's an AV of 20, and what they mean is that invisible light, like 1 in 100 million photons, won't make it to us, basically. And you can go to things like infrared, where that goes down to A of 2 for infrared, and that's sort of more like maybe, I don't know, 1 in 10 or something like that. So it's still incredibly challenging. This is not like a silver bullet. It's just very, very hard to do that. So, yeah.
Good numbers.
Good point.
All right, do you have any questions on Facebook? I have a bunch more on YouTube. Oh, in-person
Oh, yeah.
question. Sorry, we have to
An
prioritize
in-person
the people who came in person.
Kind of a silly question. Thumbs up or down on Pluto not being a planet?
Ooh, thumbs up or thumbs down?
Wait, so thumbs up.
So
if we
thumbs up
think-
means like, yay, it's not a planet, and thumbs down is boo, we wish it were a planet. On whether or not we're happy with the overall IAU consensus that Pluto is not considered a planet. I'd say it's less of a binary thing. It's more of like a gradient. So I'm like, emotionally, I want Pluto to be a planet, but rationally, when you look at the data associated with like why the distinction was made and that excluded Pluto, it seems sound. There are different ways that you can define what's a planet and what's not a planet. And we chose arguably an arbitrary definition for what makes, at some level, it's always person made, right? We all come to some sort of agreement that something is the way that it is in defining something. And that's what happened in 2005 with this International Astronomical Union decision. And there are still arguments for changing that to adapt. Like right now, that planetary definition only allows things to be called planets if they orbit around the sun. And obviously there's 5,000 objects that we've discovered around other stars that one might argue are planets, but exoplanets aren't a subcategory of planets right now. So anyway, it will probably be modified at some point in the future, but Pluto probably still won't be in it because there's so many other objects that are like Pluto in the outer solar system, and it's very different, in my opinion. And it and its brethren are very different from the kind of 8 stereotypical planets in the inner solar system. But I'm not a planetary scientist, and these other folk may have other opinions on the matter.
What do you think, planet people? Or Janosz?
No, I agree with everything Cameron said about this.
I mean, yeah, I do as well. I think also we sort of have an institutional conflict of interest because there's a guy here, Mike Brown, who wrote a book which is called How I Killed Pluto and Why It Had It Coming. And I was into that book when I was a kid, actually. But anyway,
He might beat us up with a baseball.
yeah, so we better watch our backs, right? But yeah, I mean the basic premise is historically actually, when we were discovering asteroids, we would classify those as planets, and then we just figured out there were just too many of those, and we're like, okay, well these things are just so small they should just be called something else. And it sort of seems like we've done the same thing with dwarf planets, including Pluto. And unless we want to continue classing things into that into the broad class of planet, we might not want to include it. People have said things like maybe gas giants aren't even really similar objects to rocky planets either, and so really these are all just arbitrary. Like yeah.
Yeah. Any taxonomy you come up with is going to be somewhat arbitrary in the rules that you have for the different categories, and this was created. And just so everyone's clear on what the definition, so okay, I guess I alluded to it. In 2005, an official definition was created for what defined a planet. Prior to that, we were just relying on, things that had been identified, anything that it was identified as orbiting around the sun. They were like, oh, it's a planet. Oh, it's a planet. And so finally in 2005, we came up with a formal definition. There are 3 requirements for something to have to meet in order to be considered a planet. One is it has to, as I said, it has to orbit around the sun. 2, it has to be large enough, massive enough that it's roughly a sphere. It's roughly round and ball-like. And that's really just a size scale, because when you become massive enough, gravity pulls you into a roughly perfect sphere. Obviously, we talked about how rotation can affect that. Even the Earth or the moon, they're not perfect spheres because they're rotating, so they're kind of flung out at the sides like a hamburger. But roughly, and Pluto meets those first 2 constraints. The third kind of thing that you need in order to be considered a planet is to have cleared your orbit of other similar mass objects. So the Earth goes around in its orbit, and there's no other like Earths that we're worried about running into day to day or year to year or century to century. And so that's true of all the inner rocky planets. It's true of the gas giants. But when you get out into the outer solar system where Pluto and what are known as the Kuiper Belt objects exist, there's a bunch of those guys that are similarly sized. And Pluto is potentially in danger of running into one of those. So it's not considered like the end dynamical state of the solar system out there. And eventually it could get ejected or run into something else or fall inside. And so that's why it's formally not considered a planet. Anyway, I'm being way too pedantic. So
frankly, the definition of a planet is one of the better defined definitions in astronomy.
yeah.
So
Yeah.
I'm fine with it.
Yeah.
If you look at like a lot of the stuff we talk about in galaxy observational studies of galaxies, those definitions are garbage.
It's the Wild West.
Yeah.
People are just making up names and terms and definitions. So yeah.
All right, great question.
Yeah.
Lots of discussion. Do we have any other in-person questions? Yeah, all right, yeah, we do.
No, this is great.
So these are I have 3 sort of like related ones. The rings around Saturn or any planet with rings. How big are the pieces in those rings? Like, could I go through it? Would I die if I tried? Is it dense enough that like there would be a ton around me, or would I not really see many? And then I heard that it's actually spirals, not rings. Is that true? That's the second question. Sorry. And then the third one is, what are those rings from? Are they just like moons that broke up, or are they random bits of dust?
Yeah, so the size of the particles in the rings varies. There's, I think, anything from small meter size, centimeter size to larger, probably not kilometer size. So somewhere in that ballpark. I think as far as passing through the rings, you may be a little bit worried, but probably not too much. Although I think that will depend on where you are in the rings. There are different densities of particles in different regions of the rings. As far as them being spirals, there are lots of spirals in the rings. So the waves that I talked about in my talk, those are a lot of them are specifically spiral density waves. So those are waves like if you look at a picture of the Milky Way, the big spiral or other galaxies, that's a spiral density wave, and you have the same thing in Saturn's rings. The other type of wave that I didn't talk about, well, I didn't talk about either of them, but the other types of waves that can be excited by oscillations in Saturn's rings are bending waves, and these are just like ripples in the rings. As for where they come from, so the formation of the stars usually involves protoplanetary disk. So there's a very large, expansive disk of gas and dust that feeds material inward onto the growing star. And that sort of breaks down on smaller scales for planets as well. You get circumplanetary disks that form within protoplanetary disks. And these will eventually dissipate and go away, but sometimes that can leave planetary rings. And how that works, I think, is still an open question of research. There's every so often I see a lot of papers on the archive about circumplanetary disks, and there's still a lot to be learned there. Does that answer your questions?
So is there a strict limit on how close the rings can go to Saturn or any ring system around a planet? Because it seems like at some level, it can't go all the way to the surface, presumably. Like if you've got your planet, yeah, is there an innermost stable circular orbit or just innermost stable orbit to the rings around a body?
Well, the innermost stable circular orbit, so close to a black hole, for instance, there's a closest radius you can get before things will, rather than traveling on orbits that are stable, they'll just plunge directly onto the black hole. That would be well inside Saturn or Jupiter. I don't know of any particular reason why you couldn't have rings, going close by, but there's probably dynamical reasons that I'm not familiar with.
Interesting. So you could have rings, and yeah, I'm revealing my ignorance to all the audience. You could have rings that would like start out at the surface of Saturn or whatever and extend all the way out. Maybe.
I don't really know.
But presumably it would be moving at a rate that would be differential from the surface. So that might be a limit too, but that's pretty interesting. I just don't know.
Yeah, well, so so that is one point. So one area of research that's maybe relevant here is, so accretion onto neutron stars, for instance, involves disks that go right up to the surface of the neutron star. But the Keplerian rotation is generally faster than the rotation rate at the surface of a star, because otherwise Keplerian rotation is basically this breakup rotation rate that I talked about in my talk. So unless the star is rotating at breakup, you're going to have some region of very strong shear where the rotation goes from Keplerian rotation down to the rotation of the star that's at the center. And so that produces some pretty strong boundary layer effects in neutron stars that we actually have a lot of observational evidence for. I think it's probably unlikely you'd get a similar thing on a planet, but.
So maybe that got a little bit jargony. Neutron stars are really dense balls. They're so dense that they're basically just neutrons. If you put a proton and an electron together and get them to fuse, you get a neutron. And so if something is super, super dense, almost all of the protons and electrons in it are going to sort of condense into neutrons. So it's almost entirely made up of neutrons. So Janosz is talking about stuff accreting or falling onto a neutron star, and the potential conditions for getting sort of a disk around a neutron star, which are kind of analogous to getting a ring around a planet. Does that make sense? Okay, just a quick translation. So we have a bunch of, let's do these. I think we could probably do some of these like yes or no questions. So does our galaxy's black hole have jets? From Stephen Schreier on YouTube.
Oh, it's for me. I don't think that we have any activity in the black hole in Sagittarius A star in the center of our galaxy. That's why it's been well, that's good for us because we aren't having all kinds of explosions that could have impacts on the life on Earth. But it also makes it a bit harder to study because you don't get as much information from explosions there. So no, I don't think that we do.
Yeah, I mean, yeah, I don't really think that we do either. There are things that people have been, discovering recently about our galactic center, like these gigantic Fermi bubble things, that people have observed. I don't know much about those, but in terms of like jets in the way that I imagine them, like an M87, I don't really know of anything like that.
Yeah, certainly not jets that would fling things far outside the galaxy. I think at least the picture, my understanding of the flow of gas around Sagittarius stars, that it's pretty messy, and so that may involve some outflows, but I don't think you'd get. We have evidence of the kind of collimated jets that maybe you're asking about.
Yeah, I guess we should define what a jet is.
People might think jets like
That's Cameron's interpretive dance of a jet on Earth. Does someone else want to explain what a jet is in the astrophysical sense? Nicholas or Janosz?
we were referencing it, but it's not necessarily obvious.
Maybe I could draw a picture. I guess you can't really see them very well.
Like really thick lines.
All right, I will attempt to give a qualitative description while they're doing that. So if you have material falling into something, usually a compact object of some kind, like a black hole, the material will fall in on a sort of disk. And the reason for this is because very little in the universe is not rotating. It's really hard to get something that doesn't rotate. So if you imagine something that's collapsing spherically, if you add even a tiny bit of momentum, just a tiny bit of spin, and there's no way to perfectly accrete onto a sphere, you always end up with some rotation. And so as a result, sort of like a ball of dough around a ball of pizza dough, that ends up flattening into a disk. And so every time you have some material falling onto this compact object, you almost always get something called an accretion disk. So around a black hole, material is feeding into the black hole, and through a really complicated mechanism, which I think is more or less well accepted, the Blandford's Nyack. There are a number of jet launching mechanisms that usually involve magnetic fields. But basically, you have a lot of stuff that gets really hot, and then it goes. That's my that's my scientific explanation. You heard it here first, folks. All right, some more sort of.
I want to give a thanks to the audience member who brought their own awesome dry erase marker that was better than all of our dry erase markers. So thank you, sir. Thank
Making
you.
science possible.
All right, we have a couple more sort of yes/no type questions. Let me see if I can find one. Are supercomputer simulations being done in an effort? Oh, I feel like I'm sorry, Steve, and maybe we should. I feel like I'm asking all of your questions, and I feel like I should. Let's see.
He has good questions.
Yeah, they're good. They're good questions.
I've got a question.
Oh, you got a good one? Okay, good.
I have a question. And this is just a reminder to our online audience, if you're just joining, because there are some people who are just joining, we're answering questions of you. So feel free to write your questions in whatever interface you have, and we'll try and address them. There's a question from Sanjay Sahani. By observing different galaxies in different stages of evolution, can a representative life cycle of galaxy be determined or estimated? And that's an excellent question, because we see, 100 billion galaxies. And as we discussed before, they're all roughly at a snapshot in time. We don't see them actively moving. It's just a moment in their time. And even if we watch it for days or years or whatever, we aren't going to see any substantial change. So, but we see them, and we see so many different instances, we can sort of piece together how one might change into the other, especially with the aid of some of these computational models. Do you want to? Okay, I'll start. We don't have a comprehensive model yet for how kind of the life cycle of a galaxy, but the example that I always use is this. So pretend for a moment that you are an alien who experiences the entirety of your life cycle in a millisecond. So you fly around on your super speedy spaceship and you fly down to Earth, and you don't have a context for how humans live or die or age or anything like this. So you're zipping around and you're flying, and you fly next to some people and next to other people, and you have all these observations. But from your perspective, because remember, you live your entire life cycle in one millisecond, from your perspective, everyone's frozen in time. So you catch everyone at different stages, and you might see infants, and you might see adults, and you might see elderly people, but you don't necessarily know, of course it sounds absurd to us, that you wouldn't necessarily know that an infant grows up to be an adult that grows up to be an elderly person. You might think naively, because again, you have no context, that it might be the reverse or something else. But what's even more kind of challenging is maybe an infant is an infant for their entire life and they never become one of these other stages. So really what it's your job to do is identify, are infants their own organism and they never change to one of these other life cycles? Are they totally distinct, or does one change from another? Similarly, when you see men or women, are these distinct organisms, or is it just a natural life cycle that a man would eventually turn into a woman, or vice versa in a natural sense? And so, of course, again, that sounds a bit peculiar out of context, but without the context of living in our society, you wouldn't necessarily have a good feasibility for like how these transitions would work. And so it's the same thing with galaxy evolution. Now, some of the things that we have identified, first of all, the kind of main categories that we find for galaxies. We find, as I described, galaxies like our own Milky Way, disk galaxies or spiral galaxies that consist of kind of a disk of material and then a bulge of material in the center. When I say disk and bulge, it's mostly gas and stars that make up those different components that we see visually. So that's kind of one category of galaxy. Then there's elliptical galaxies, which are more like, I really like eggs, so I use eggs as my example. Hard-boiled, it's like a hard-boiled egg. It's just a single component that's kind of in an oval. It's kind of in an ellipsoidal shape. And those are kind of the two primary categories of galaxies. And you can definitely have disk galaxies that eventually form into elliptical galaxies, the hard-boiled ones, based on the environment in which they find themselves. If they're around a lot of other galaxies, there tend to be dynamical interactions between them where they cancel out the rotation. So if you slam together two disk galaxies like the Milky Way that are each rotating in the opposite direction, their angular momentum, their rotation kind of cancels out, and they eventually just form into a system like one of these elliptical systems. So as a good example of that, that is the sort of system that's going to happen at the end of, in 8 billion years, when the Milky Way runs into the Andromeda galaxy. You're going to have two of these disk systems. They slam into each other. There's some really nice videos of this online that you can find, and they're going to cancel out their angular momenta, and you're going to end up with this ellipsoidal looking galaxy. But it doesn't always necessarily go that direction. We do find some circumstances where you can spin up galaxies under the right conditions. And yeah, it's like I said, we can see some of the mechanisms at work, but we can't necessarily see, we don't have a global model that unifies everything together. Do you want to add on that?
Sure, yeah. So stars are, compared to galaxies, relatively simple. With a couple of equations, you can actually model more or less the overall life cycle of a star from start to finish. Galaxies are just a lot more complicated. You have not only billions, up to billions of stars running around and doing things. Stars don't run, I don't know what I'm saying. But you also have gas, and you also have dark matter, which we mostly understand from an observational perspective, but we haven't directly detected. And putting all of those together is really hard, especially when you add like gas and dust and things. Gas is really, really difficult to model. And so that makes things complicated. So I think another good analogy for galaxies is thinking about forests. So forests are entire ecosystems. They have generations of trees that live and die within them. And that's sort of what a galaxy is. It has generations of stars that are living and dying within them. And so you can't really think of a life, there's no standard life cycle of a forest, right? And there's no standard life cycle of a galaxy, because the galaxy, will have many generations of stars, or maybe just one or two, depending on the conditions inside of it. But galaxies will also interact with each other. So a forest will interact with its surroundings and might be bigger or smaller because of that. So that can also affect how galaxies evolve. So yeah, galaxies, super complicated. That's why I like them.
That's a great, I really like eggs because eggs are tasty, but that's a good, I like that tree forest-based analogy there.
All right, and I think your answer about Andromeda and the Milky Way colliding was a question that we had on YouTube. So thanks for that.
Oh, okay, well, hooray.
All right, and then
Case
we have
closed.
another question. Wait, oh shoot, I just had it. Okay, this is another black hole question. So does Sagittarius A star, the black hole in the center of a Milky Way, revolve due to resultant centripetal force due to surrounding star? So this is from Girish Ananda on YouTube. does it revolve due to the centripetal force of surrounding stars?
So Sagittarius A star has a lot of stars around it that are moving really rapidly. But it's actually pretty difficult to spin up black holes. It takes a really long time and a lot of angular momentum from the surrounding gas and stars. So I don't know exactly how much Sagittarius star's spin is affected by its surroundings, but it's probably not a huge effect.
Just to confirm, in order to spin up a black hole, you can't do it just by the environment, like something speeding by. It actually has to accrete the object. Like if this microphone is the silver part of the microphone is my black hole, I can't just invoke a spin by having stuff orbit, right? I mean, I guess maybe, but not very much. It actually has to absorb something's flying by and it falls in and it carries with it that angular momentum that causes it to spin up more.
Yeah.
And that just takes a long time because it's so much more massive than those individual stars. It's like little Cheerios flying by a bowling ball. And I've got all the analogies here, all food-based analogies. So you got a bunch of Cheerios flying into a bowling ball, and then they very slowly can spin it up, but it's going to have its own rotation pretty well defined, right?
Yeah, it's probably not going to change very much. It is theoretically possible for you to spin up a black hole
with Cheerios.
Yeah, by not dumping things onto it, because spin is, when something spins, we call that angular momentum. And, you can get that from an object which is sort of whizzing by, but this is just so little angular momentum, right? I think there was a result like when we imaged, when the Event Horizon Telescope imaged Sagittarius star, I think they claimed that they detected that it was spinning. Is that right? Do you remember this?
I don't.
I think they're still deciding on
Yeah,
some parts of the
it
analysis.
might be wishy-washy, right? But there was some statement that it might have, there might have been some detection of a spin, maybe. This is, I think, likely to be from its formation if it's there, probably not from just passively things around it. Yeah.
Cool. All right. Do you have any questions, or I can do some more?
I have a deeper question, but maybe we'll save it for a few minutes.
All right. So we're going to save a deep question. Do we have any other questions from our in-person audience? Yeah.
Of the objects in our solar system besides Earth, which, if any, objects do you think have life on them, even microbes?
That's a dope question. Let's see.
Planets, come on.
Yeah.
Galaxies don't have life. I mean, maybe.
All right. There's a moon that we're pretty sure has life, right?
Oh, well, we don't know that. We're not pretty sure that
We're not
anywhere
pretty
has
sure.
life except here.
Okay, fair.
But there are places in the
Different
solar
conditions that are-
system where, Europa, which is one of the Galilean moons of Jupiter, and then there's also recent talk of Enceladus, which is I think one of Saturn's moons. These are these are kind of very interesting environments where we expect life, like our conception of life could potentially exist. We've never detected anything there because this is very hard to do. But the idea with Europa is that it's one of 4 Galilean moons. Which orbit around Jupiter, and they sort of tidally interact a lot with the planet and also with each other. So they're sort of like pushing and pulling on each other and heating up. The innermost one is Io, and Io is just like totally on fire. Like it's always like covered in volcanoes. It looks like a pizza.
Awesome.
Yeah. And the second one out is Europa, which is like it's like an ice planet. Like you look at it and it's just like smoothed over with ice. But the idea is that the tidal heating could sort of melt the inside and you have a liquid ocean. With Enceladus, you actually see like streams, like geysers, which indicate that there's water there. So people,
What's ice
yeah.
Yeah. So, and as Nicholas is saying, so Enceladus, it's ejected. It's an icy surface planet in the same way that Europa is, but it's actually expelling ice off the surface, and we've caught observations of imagine a volcano that's erupting so much that it's kicking like lava up and it goes flying off this, like becomes gravitationally unbound and goes into space. That's kind of what's happening with Enceladus, but it's these ice geysers that are launching ices up into the ether, you know. I'm sorry, I didn't mean to interrupt. But yeah, so the idea is that potentially life could exist maybe in these. We think that water is really good for helping the chemical reactions that led to the presence of life here on Earth. So we look for other systems, whether it's in the Goldilocks zones around other star systems where exoplanets sit, where if there were water present, it would be liquid water. We look for that and say, oh, maybe that's a place where it could happen. But we don't really know, right?
Yeah. We could do a little bit of speculative fiction, right? And say, you know, we're kind of biased. You know, we think that life needs water because that's the only life we've ever seen before. There's like people who will say like, oh, you know, Titan like is a planet where you basically have like oceans or like lakes and you have like, you know, sort of a surface, but the role of rock is instead played by ice and the role of water is instead played by like, you know, methane or like natural gases basically. And so I don't know, like, we don't know how life would work if it were that, but maybe.
But I mean, we are starting to become more sensitive to detecting life on Mars, for instance. This is one of the big goals by having all the exploration on the surface of Mars, is to be able to be sensitive to, you know, was there water on the surface at some point in the past? The evidence seems to point towards yes. And could we be able to find the evidence for either current microbial life there or some sort of, you know, past microbial life that's there? And that's a big push in a lot of the exploration that's going there. But Mars is really the only place we've spent any substantial amount of time exploring and taking data. So there's a lot left to see in our solar system, let alone all the other stellar systems that we're only observing through the light that we get through our telescopes.
Cool. So we have sort of a more observational astronomy question. We have a couple actually. So first, as our solar system moves through the galaxy, is it possible that in a distant future we will have a different set of constellations? I think the short answer is yes. That is likely. It's happening now. Our constellations are changing, but very slowly.
Yeah, I don't know if how much more there is to say about that. I guess you know, people do like measure what are called proper motions. Those are the motions of stars across the sky, you know, not you know, towards us or away from us, but in a way that we can see. You can like sort of look at things that are nearby and measure those things. And it stands to reason that they would keep going. So yeah. And
just to make it clear, I mean, this is probably obvious to everyone, so it's probably unnecessary. Most of the things I say are unnecessary. The distribution of stars in space is like a three-dimensional distribution of those stars. Of course, when we look from within, like one of those star systems, the solar system, looking up, everything is flattened onto two dimensions, the two dimensions that we see on the sky. But when we look up, you know, just like when we look up the lights above us, you can't necessarily tell that those two lights that are right next to each other are physically right next to each other. Or if one is like, you know, one of those stars is a mile behind the other one, they just appear right next to each other. And it's the same thing as we move and all those other stars are moving, which are what define our constellations, to the constellations will change over time. So yes, we do see these things changing. The North Star wasn't the North Star like 2000 years ago. There was nothing where there was no light, no star that coincided with the rotation, the rotational pull of the Earth's rotation. So it's actually just kind of a cosmic coincidence right now in time that when you look at the place where the Earth's rotational pole is, it coincides with a reasonably bright star. But that won't be the case in 2000 years, and it wasn't the case 2000 years ago.
So when the dinosaurs were around, we were actually on the other end of the Milky Way, and they saw totally different constellations. So dope. Galactic archaeology, a different kind of galactic archaeology. All right, we have another question from YouTube, sort of related to observational astronomy. Sort of astroarchaeology. Okay, ancient structures like Stonehenge, Newgrange, and Mesopotamian ziggurats were regarded as observatories. How accurate were they? Yeah, that's a good question. I mean, from everything I've read, it seems like they were accurate for what they were designed to do. But I would argue that since the development of CCDs, or charged coupled devices, which are the things that are used to take like phone camera pictures, basically, they were super helpful because we were for the first time able to like quantify how much light was coming in. So before you had like these photographic plates, and before then you had to use the naked eye, which is why the ancient Greeks came up with a truly terrible system for measuring how bright a star is, which is based on the naked eye. So it's like logarithmic in scaling. It's terrible. Anyway, if you ever take an astronomy class, I'm so sorry. That's probably one of the things you'll have to learn. But ever since we've developed these charge coupled devices that actually measure exactly how many photons are coming in, we've been able to do a lot more precise measurements of basically everything. So I would say they're probably precise for things like tracking the motion of the sun in the sky, which is probably all you really needed to know. I mean, it's useful for a lot of stuff. Yeah, if you want to know seasons, if you want to know, when it's time to move to another place, or, sacrifice a goat or whatever. I don't know what they did in these ancient societies.
Required a lot of precision to know that. Yeah.
Yeah. So, okay, so that's a good question, actually. I mean, it's worth looking into. I actually don't know how precise they were. Are supercomputer simulations being done in an effort to determine what happens with the interior of a black hole with quantum mechanics?
I guess I don't know. It's not really the domain of astronomy to simulate the inside of a black hole, I guess. And even if it were, so there are groups here that do simulate very extreme space times. There's actually a group here called the simulating extreme spacetimes group, which is the SSS group. This is a kind of field called numerical relativity, where you just solve Einstein's field equations, and this is usually used to simulate like merging black holes. But from talking to the my friends in that group, people usually just cut out as much of the inside of the black hole as they can because nothing comes out of it, so no one cares about it. And just using codes like that don't really work because you're always, basically simulation requires that you know what the laws of physics are. And if we don't know what the laws of physics are, then we can't really simulate, how those things.
So really quickly, a major issue is that black holes are, for the most part, the behavior of black holes is described with Einstein's general relativity. Quantum mechanics and sort of the other end, particle physics end of physics, doesn't mesh with general relativity at all. Like you get some weird inconsistencies that no one has been able to solve yet. So understanding how gravity works on the largest scales through general relativity, and understanding how all of the other fundamental forces in nature work, especially on the smallest scales, no one has done that yet. No one has come up with a truly unified theory of all of these things. So, oh yeah, hold on, we have a question from in-person audience member.
Yeah, so you mentioned that nothing really comes out of the black hole. So like there have been radio flares and jets being seen come out from like the plane perpendicular to the black hole's like disk. So like, do you have any idea where and how that originates?
Great question. So this is getting back to the jets coming out of a black hole that we talked about a little bit earlier. So that's what this picture, which is it's visible on the screen. So that's what this picture represents. Do you want to give a quick recap, Janosz?
So this isn't really my area of expertise, but we were talking a little bit earlier how generally onto a black hole, gas will move inward through what's called an accretion disk. And this generally involves fairly slow motion as gas will spiral inward. But as stuff gets really close to a black hole, everything gets heated up really, really hot and things move really, really fast. And there are a few different mechanisms, mostly involving magnetic fields, that lead to launching of jets close to the center of these accretion disks. Again, this isn't really my area of expertise. I don't really have much more of an explanation than that. Does anybody else?
Oh, I don't know what the question, but it sounds like you did a good.
Yeah. All right. Oh yeah, great.
I'm sure that the answer to this has been calculated, and I don't expect you guys to know it off the top of your head. I'm just kind of more curious in hearing you guess. Do you think that there's more mass within galactic space, like intragalactic space, than there is in intergalactic space? If you had to order of magnitude it?
Yes. So is there more, like you're talking like in between stars inside of our galaxy versus in between stars outside of our galaxy, something like that? In the voids within the galaxy versus the voids outside of our, well, I guess most of the voids are in between galaxies. So yes, there's more stuff. I mean, okay, so the places where there's the most stuff are in the condensations, the planets, the stars, those like kind of structures. But there's a lot of space in between those condensations in the broader like universe. But even in our galaxy, which itself consists mostly of empty space in between those stars and in between those planets and in between the black holes and those structures within the galaxy, the density of material is higher than the space in between galaxies themselves. Even though galaxies, as I said, are mostly empty space, but there's still more stuff in that by a factor of, I think like 1,000 or 1,000,000. So
for scale, the average distance between any two stars in the Milky Way is approximately 1 parsec or 3 light years. When you start looking at the distances across these massive voids in the universe
between galaxies,
that can be much larger. So the biggest, emptiest voids in the universe, in the nearby universe, are in the order of 10 million times that distance between stars. So space is real empty.
Yeah, it's real empty, real empty. We're reaching the end of our time. Are there any super pressing? I have our deep one that we can kind of.
I have a fun one that we can finish
a fun
on.
one. Okay, that sounds
Or
good.
we could do a deep one, either way. What are the panelists' favorite science fiction films? So this person likes, this is Stephen Schreier on YouTube, likes Interstellar by Kip Thorne, who is here at Caltech.
Yeah.
And Carl Sagan's Contact.
Oh, yeah.
I personally do not like Interstellar, but that is because I have a weird personal vendetta against Matthew McConaughey. I don't like him.
You hate Matthew?
I don't like him.
All right.
No, I just, something about him.
Okay.
I feel really bad. Like I really wanted to like Magic Mike, but I don't like Matthew McConaughey.
Wait, is he in that?
He's in Magic Mike.
Oh, I've never seen that.
Okay. Anyway, so I don't like Interstellar very much. I think Contact is a good movie.
Yeah. Whoa. I think Contact is a great film. And it also has Matthew McConaughey.
No, it doesn't.
Yes, it does.
No.
Yes, it does.
Maybe I just haven't seen it in a really long time.
He plays,
No!
yeah. He's like an old, yeah, well,
Okay, well,
I'm
in that
sorry, I
case,
just ruined that film for you.
In
But
this case, I like The Martian. There we go. That's my
okay,
favorite
The Martian's
film.
pretty good. Favorite science fiction film. I mean, I just talked about the science of Star Wars. I really like Return of the Jedi. I really like Empire Strikes Back. Even
Cameron-
though those are like not as science accurate as perhaps ones written by a Nobel laureate like Kip Thorne or an excellent science communicator like Carl Sagan or something like that. The Martian was really good. The science in The Martian is overwhelmingly accurate. You know, Andy Weir wrote that book. So okay, the film that The Martian is based on is the film The Martian is based on a book that was written by this guy Andy Weir. And when he was writing the book, he basically crowdsourced the science in the book he was writing it and then he put it out on like forums on, I mean, this is before Reddit, I think. So he was just putting it on forums, and then scientists and engineers would write back and be like, oh, no, you can't do that. That's not accurate. And so he'd modify the story. So it was kind of like an open source book that he wrote. And then for a long time, it wasn't even published. I downloaded the text file before it was actually published, and I had the text file and I read it and I was like, oh, that was a really good book. And then evidently some publisher did too. And they read and they were like, oh, we'll publish this. And then it became, a bestseller and turned into a film. But yeah, I think that's a cool way to write a book, is like, just get other people to correct your mistakes for you. No, The Martian's really good. What's jumping to mind are movies that aren't good science fiction. Has anyone seen Event Horizon? It's like a horror movie where a spaceship uses a black hole event horizon to go fast, but then it causes like people to go insane and there's murders on the ship. It's, oh man, I can't recommend that film. But you guys give your recommendation.
Yeah, I'm probably gonna be pretty boring. So I'd say Interstellar and Martian are things that I like. I did have a professor who took great issue with Interstellar, not because there was anything really super scientifically wrong with it, but he was a theater minor, so he was like, he took issue with Matthew McConaughey's acting. He's like, this is not how people talk, and it's like, I guess this is like, I mean, he's not a professor in theater, but you know. Anyway, I like it. I've watched it many times. Would recommend. But
So I also like The Martian. So that's a great movie. Moving away from movies, I also really like the Expanse TV show. That's similarly not necessarily entirely accurate, but for the most part plausible vision of space travel in the next few hundred years. So it's a cool show.
Have people seen the Foundation television program? Did you enjoy it? I haven't really, I watched one episode and it seemed cool. I mean, the books are super good. Asimov is like great. And that's one of his, the acting is very good. Yeah. So Foundation, I mean, that's not a movie, it's a television program, but still it's kind of interesting. A new rendition on a classic science fiction. Okay. Well, we've reached the end of our time tonight. Thank you, audience members who stuck around with excellent questions. Thank you, online audience members who stuck around and asked some wonderful questions. Yeah, so just quick conclusion notes, closing remarks. Our next event will be Astronomy on Tap. If you're here in the LA area, I encourage you to go. It will be our first in-person Astronomy on Tap since before COVID. It will be a week from Monday, June, whatever the heck that is. I think it's like June 12th or something, 11th or 12th. It's Monday in a week and a half. And we'll also do it Wednesday in a week and a half. They will be in Pasadena at a bar called the Dog House. They will be outdoors, so you don't have to worry as much about COVID, which is nice. And the beer's pretty good. And it will coincide with a bunch of events for the Pasadena City of Astronomy the Saturday prior to that. I'll post this all on our website and such. There's a bunch of stuff, free stuff happening at the Pasadena Convention Center with talks going on. We're going to set up solar telescopes to look at the sun. We're going to light some marshmallows on fire with mirrors pointed at the sun. Who doesn't like burned marshmallows from the sun? Free marshmallows. There'll be a bunch of like cool things. Infrared camera, so you can see what you look like in the infrared, like, you know, thermal goggles if you're in the military or whatever. So lots of cool stuff. And then our next stargazing lecture like this will be again in person. It'll be a month from now, and I haven't figured out who or when or what, but stay tuned. And yeah, that's it. Now I have to go stop this live stream. Thanks, everybody.